Somewhere across the galaxy, a giant star runs out of fuel and its core collapses in less than a second. What happens next is the most violent event the universe has produced since the Big Bang itself. Twin beams of pure energy erupt from the dying star's poles, racing outward at very nearly the speed of light, each one carrying more power in a few seconds than our sun will release in its entire 10 billion year lifetime. This is a gamma ray burst, and here is the part that should unsettle you. It is not an explosion that spreads in every direction. It is a beam, a searchlight, a cosmic rifle that fires into one narrow cone of space and ignores everything else. Most of the universe never even notices it happened. But if you happen to be standing in front of the barrel, nothing about your world survives unchanged. Before we go further, if this is the kind of thing you find fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Picture the moment of the burst itself. Far across the galaxy, or perhaps in a galaxy so distant its light left before our sun was even born, a star many times more massive than our own reaches the final second of its life. For millions of years, it has been fighting a quiet war against its own gravity, fusing element into heavier element in its core, holding itself up against the crushing weight of all that mass, and in the space of a single heartbeat, it loses. The core collapses inward faster than you could blink, falling in on itself until it forms something dense and dark and impossibly hungry. And then, from the poles of this newborn monster, two beams of energy erupt outward, not gently, not slowly. They tear out of the dying star at more than 99.9% of the speed of light, carving through the star's own outer layers and racing into open space. This is what a gamma ray burst really is. And the single most important thing to understand about it, the idea that everything else in this story depends on, is that it is not an explosion that goes off in all directions at once. It is a beam. Two beams, actually, fired in opposite directions like the twin barrels of a cosmic rifle. The energy does not spread out evenly across the sky the way light spreads from a candle. It is squeezed, focused, collimated into a narrow cone perhaps only a few degrees wide. And that one fact changes absolutely everything about how dangerous these objects are, how we see them, and why a single one of them could be either the most spectacular light show in the universe or the end of life on a planet, depending entirely on which way it happens to be pointing. Let me give you a sense of the raw power we are talking about, because the numbers are almost difficult to take seriously. In the few seconds that a typical gamma ray burst is firing, it can release more energy than our sun will produce in its entire lifetime. And our sun is not a short-lived star. It has been shining for about 4.5 billion years already, and it has roughly 5 billion years of fuel left. So take 10 billion years of steady, relentless sunshine, every photon the sun will ever emit, and compress all of that energy into something like 10 seconds. That is the scale of a gamma ray burst. Some of the most powerful ones release in as brief moments more energy than 100 billion ordinary stars pouring out their light together. If you tried to measure the total energy of a strong burst, you would be dealing with numbers like 10 to the 47 joules, or in some extreme cases, even more. That is a 4 followed by 47 zeros, give or take. For comparison, the entire human species, across all of recorded history, using every power plant, every engine, every fire we have ever lit, has produced a vanishingly tiny fraction of that. We are not even a rounding error. A gamma ray burst is the single most luminous kind of event we have ever detected anywhere in the cosmos. And for a few seconds, a single one of them can briefly outshine everything else in the observable universe put together. And here is where the story takes its first strange turn. Because for the longest time, nobody had any idea these things existed at all. They were not predicted by theory. No astronomer sat down with equations and announced that the universe should be producing these flashes. We stumbled onto them completely by accident, and the way we found them is one of the stranger tales in the history of science. The year was 1967, and the world was deep in the Cold War. A few years earlier, in 1963, the major nuclear powers had signed a treaty agreeing to stop testing nuclear weapons in the atmosphere and in space. The problem with any treaty, of course, is trust. How do you make sure the other side is actually keeping its promise? You cannot simply take their word for it. So the United States launched a series of satellites designed specifically to catch anyone cheating. These were the Vela satellites, and their job was to watch for the telltale flash of gamma radiation that a nuclear detonation produces. If anyone set off a bomb in space or in the upper atmosphere, these silent watchers would see the burst of gamma rays and sound the alarm. The Vela satellites did their job. They watched the Earth, they watched the sky, and they recorded the gamma ray flashes that came their way. But the scientists analyzing the data began to notice something that made no sense at all. They were detecting flashes of gamma rays, yes, but the flashes had the wrong shape. A nuclear explosion produces a very particular signature, a sharp spike followed by a specific kind of fade. These mystery flashes did not look like that. They had complicated, irregular profiles, sometimes with multiple peaks, that simply didn't match any bomb. And even more puzzling, when the scientists worked out the directions the flashes were coming from, the answer was not the Earth at all. They were coming from deep space, from out among the stars. A researcher named Ray Kleber-Sedel and his colleagues at Los Alamos spent years carefully studying these signals, ruling out every mundane explanation they could think of. It was not the Soviets. It was not the sun. It was not any known phenomenon. By the time the work was finally declassified and published in 1973, the conclusion was both thrilling and baffling. The universe was producing brief, intense flashes of gamma radiation, the most energetic form of light there is, and we had absolutely no idea what was making them. A secret military project designed to police nuclear weapons had accidentally discovered one of the most violent phenomena in all of nature. Now, the moment you accept that these flashes are real and that they come from space, you run straight into a question that would torment astronomers for the next quarter of a century. How far away are they? Because the answer to that question determines everything else. A flash that looks bright in our detectors could be one of two very different things. It could be a relatively modest event happening close by, or it could be an utterly cataclysmic event happening enormously far away. A candle held up close and a lighthouse seen from across the ocean can look equally bright to your eye, but they're not remotely the same thing. Without knowing the distance, you cannot know the true power. And without knowing the power, you cannot even begin to guess at the cause. This led to what astronomers came to call the Great Debate over gamma ray bursts, and it split the community for years. One camp argued that the bursts were relatively local, happening within our own Milky Way galaxy, probably involving neutron stars somewhere in the galactic neighborhood. If that were true, the energy involved would be large but manageable. the kind of thing our existing physics could comfortably explain. The other camp argued something far more radical. They suspected the bursts were coming from billions of light years away, from the far reaches of the observable universe. And if that were true, the energy required to make them appear as bright as they did would be so monstrous that it pushed the limits of what anyone thought was physically possible. For a long time, there was simply no way to settle the argument, because gamma rays are frustratingly difficult to pin down. Ordinary light, the kind your eyes use, can be focused with lenses and mirrors. You can build a telescope, point it at a source, and see exactly where the light is coming from with beautiful precision. Gamma rays refuse to cooperate. They are so energetic that they punch right through lenses and mirrors rather than bending the way visible light does. The early gamma ray detectors could tell you that a burst had happened and roughly how much energy it carried, but they could only point to a large fuzzy patch of sky as the source. Imagine someone fires a gun somewhere in a stadium, and all you can say is that it came from somewhere in the northern half of the building. That is not enough to find the shooter. And it was not enough to find the source of a gamma ray burst. A major step forward came in 1991, when NASA launched the Compton Gamma Ray Observatory, an enormous orbiting laboratory carrying an instrument specifically built to catch and catalogue these bursts. Over the years that followed, it recorded thousands of them, building up a map of where they appeared in the sky. And that map turned out to be the first really decisive clue. Because if the bursts were coming from within our own galaxy, they should have been concentrated along the band of the Milky Way, that bright stripe of stars you can see arching across a truly dark night sky. Our galaxy is a flattened disk, and we sit inside it. So galactic objects tend to cluster along that disk from our point of view. But that is not what the map showed. Instead, the bursts were scattered completely evenly across the entire sky, in every direction, with no preference for the plane of the Milky Way whatsoever. They came from above us, below us, and all around us in perfectly uniform fashion. This even spread what astronomers call an isotropic distribution, was a powerful hint. It strongly suggested that the bursts were not tied to the structure of our galaxy at all. They looked like they were coming from the universe as a whole, from a vast spherical shell surrounding us in every direction, which is exactly what you would expect if their sources were spread across the distant cosmos. The local camp began to lose ground, but the argument was still not truly over, because a map of directions alone could not nail down the distances. To do that, astronomers needed to catch a burst in the act and trace it to a specific object. The breakthrough that finally cracked the mystery wide open arrived in 1997, and it came from an Italian and Dutch satellite named Beppo-Sachs. The problem with gamma ray bursts, remember, was that they were over in seconds. By the time you swung a regular telescope toward where one had happened, the gamma rays were long gone, and there was nothing left to see. But scientists had begun to suspect that the burst itself might not be the whole story. Perhaps after the initial flash of gamma rays faded, the source left behind a fainter, longer-lasting glow in other kinds of light. An afterglow that lingered for hours or days. If such an afterglow existed, and if you could find it fast enough, you could finally point an ordinary telescope at the right spot and see what was actually there. Beppo-Sachs was clever because It could do something earlier instruments could not. When it caught a gamma ray burst, it could quickly determine the position with far better accuracy than before, narrowing the source down from a huge fuzzy patch to a small, manageable region of sky. And then it could swing its own X-ray instruments to look at that spot within hours while the afterglow was still glowing. In 1997, this is exactly what happened. A burst went off, Beppo Sachs pinned down its location, and for the first time ever, astronomers caught the fading X-ray afterglow. They sent the coordinates to telescopes around the world, which then captured the afterglow in visible light as well. And when those telescopes looked at the precise spot where the burst had occurred, they saw something that ended the great debate forever. They saw a faint, distant galaxy. That afterglow turned out to be a phenomenon worth understanding in its own right, because it behaved in a very particular and revealing way. The initial burst of gamma rays was gone in seconds, but what it left behind faded slowly, and it faded across different kinds of light in sequence, like an echo rolling down through the spectrum. In the first hours, the afterglow shone most strongly in X-rays, the next most energetic form of light below gamma rays. As the X-rays dimmed over the following hours and days, the glow shifted downward into visible light, the kind our eyes and ordinary telescopes can see. And then, over the days and weeks that followed, as the visible glow itself faded away, the afterglow lingered longest of all in radio waves, the least energetic light of all. This orderly march from gamma rays to X-rays to visible light to radio, fading and cooling as it went, was not random. It was the signature of something that had been violently energized and was now slowly relaxing, shedding its energy in ever gentler forms as it cooled, and tracking it across all these kinds of light gave astronomers a rich and detailed record of the aftermath that the brief gamma ray flash alone could never have provided. But the single most important thing the afterglow delivered was a distance, and the way it delivered one is worth appreciating, because it is the method by which astronomers measure the reach of almost everything in the distant universe. When the visible light afterglow was captured, and when the faint galaxy hosting it was identified, astronomers could spread the light from that galaxy out into its component colors, the way a prism spreads sunlight into a rainbow. Woven into that spread of color are specific features, particular wavelengths where certain elements absorb or emit light, appearing as sharp lines at fixed, known positions. These lines are like a fingerprint, identical everywhere in the universe, because the laws of physics that produce them are the same everywhere. And here's the crucial point. In the light from a distant galaxy, those lines are not found at their normal positions. They are all shifted, slid together toward the redder, longer wavelength end of the spectrum. This is the famous redshift, and it happens because the universe is expanding. As light travels across the vast stretching cosmos toward us, the very space it moves through expands beneath it, stretching the light's wavelengths along with it. The farther the light has traveled, the more space it has crossed, and the more its wavelengths have been stretched. So, the amount by which those fingerprint lines are shifted tells you directly how far the light has come. When astronomers measured the redshift of the galaxy hosting that first afterglow, the lines were shifted by a large amount, and the meaning was unmistakable. The light had been stretched by crossing an enormous expanse of expanding space. The galaxy and the gamma ray burst within it lay billions of light years away. There was no longer any room for argument. No way to place these events comfortably within our own galactic neighborhood. The redshift was a ruler laid across the cosmos, and it read out a distance that settled the great debate in a single measurement. The afterglow was sitting in a galaxy billions of light years away. By analyzing the light from that galaxy, astronomers could measure how much the expansion of the universe had stretched it, and from that, they could calculate the distance. The answer was staggering. These bursts were not local at all. They were happening across the entire observable universe, often billions of light years from Earth, far beyond our own galaxy, far beyond even the nearest galaxies. The distant camp had been right all along, and that answer, while it resolved one mystery, immediately created a far deeper and more troubling one. Because now, do the arithmetic. If a gamma ray burst appears as bright as it does in our detectors, and if it is sitting billions of light years away, then the actual, true amount of energy it must be releasing is almost beyond comprehension. Brightness fades with distance in a very specific way. The farther away a light source is, the more its light spreads out before reaching you, and the dimmer it appears. So for something billions of light years away to still register as a powerful flash in instruments here at Earth, the original event must have been releasing energy on a scale that frankly seemed impossible. When astronomers worked out the numbers, assuming the burst was shining equally in all directions like an ordinary star, they got values so enormous that they ran into a wall. To release that much energy in every direction at once, in just a few seconds, you would need to convert the entire mass of something like several suns completely and instantly into pure radiation. Even the most violent stellar deaths we knew about, the explosions of supernovae, did not come close to producing that much energy that quickly. The numbers simply did not add up. Something was wrong. And this is the precise moment where the central idea of our entire story rides in to save the day. The flaw in the calculation was a single hidden assumption, an assumption so natural that nobody initially questioned it. Everyone had assumed that the burst was shining in all directions equally, like a light bulb or a star, radiating its energy outward in a complete sphere. But what if it was not? What if the energy was not spreading out in every direction at all? What if, instead, it was concentrated into a narrow beam, fired into one tiny cone of space while leaving the rest of the sky completely dark? This changes the math entirely, and it changes it by an enormous factor. Think about the difference between a bare light bulb and a laser pointer. A light bulb takes its energy and throws it out in every direction, lighting up the whole room. To make a light bulb appear blindingly bright from a great distance, you would need it to consume a tremendous amount of power, because most of its light is going off in directions you will never see. A laser pointer is different. It takes a tiny amount of energy, just a few thousandths of the power of that light bulb, and concentrates all of it into one pencil-thin beam. If you happen to be standing directly in the path of that laser, it can dazzle you, even blind you, despite the fact that the laser is using almost no power at all. The trick is focus. The laser is not powerful, it is concentrated. A gamma ray burst, it turns out, works far more like the laser than the light bulb. The energy is not radiated out in a full sphere. It is funneled into those twin narrow cones streaming from the poles of the dying star. When astronomers redid their calculations taking this beaming into account, the impossible energy numbers suddenly became merely extraordinary. If the burst is only firing into, say, a cone covering a few degrees of sky rather than the entire heavens, then the true energy required drops by a factor of hundreds, sometimes 1,000 or more. The event is still one of the most powerful explosions in the universe, make no mistake, but it is no longer physically impossible. It fits within the bounds of what dying stars and colliding remnants can actually do. The beam saved the theory, but the beam does something far more important than just rescue the arithmetic. And this is the heart of why these objects matter so much, and why this story is ultimately about a threat. Because if a gamma ray burst is a beam, then direction becomes everything. An ordinary star shines on everyone. Stand anywhere around it, and you receive its light. But a beam ignores almost everyone. It points one way, and only the tiny sliver of the universe that happens to lie within that narrow cone ever receives the full fury of the blast. Everyone outside the cone, which is to say nearly the entire universe, sees nothing at all, or at most a faint glow if they are off to the side. The burst could be firing at this very second from a nearby star. And if its beam is angled even slightly away from us, we would never even know it had happened. And this leads to a consequence that is both humbling and a little unsettling. The gamma ray bursts we actually detect, the thousands we have catalogued over the decades, are only the ones whose beams happen to be pointing at Earth. For every single burst we see, there are hundreds of others firing in directions we will never observe, their beams sweeping out into empty space, missing us entirely. The universe is crackling with these explosions far more often than our catalogue suggests. We are simply only catching the ones aimed in our general direction, like standing in a vast field of lighthouses and only ever noticing the few whose beams happen to rotate across your eyes. The true rate of gamma ray bursts in the cosmos is far higher than the rate we observe, precisely because most of them are pointed somewhere else. So we are left with a beautiful and slightly menacing picture. Scattered across the universe, stars are dying and remnants are colliding, and each time one does, it can fire a beam of gamma radiation so intense that for a few seconds it shines brighter than everything else in its galaxy put together. These beams race across space at very nearly the speed of light, narrow and focused and lethal. Most of them we never see. The ones we do see, we see precisely because their beams found us across billions of light years of darkness. And that raises the question that will haunt the rest of this story. If these beams are out there, slicing through the cosmos in every direction, and if being inside one means receiving the full, undiluted force of the most powerful explosion in nature, then what exactly would happen to a world that found itself standing in front of the barrel? What happens to a planet, to an atmosphere, to living things, when one of these searchlights swings across them and locks on? That depends entirely on what makes the beam in the first place, and on how something as chaotic as a collapsing star manages to focus its dying scream into a cone so narrow and so straight. Because a beam this tight does not happen by accident. Nature does not casually produce a searchlight out of an explosion. There has to be a machine at the center, an engine of staggering power and precision, taking the raw violence of a stellar death and squeezing it, channeling it, accelerating it to within a whisker of light speed, and aiming it like a rifle. And remarkably, the universe has not one way of building such an engine, but two completely different ways, born from two completely different kinds of cosmic catastrophe. Understanding how those engines work, how a black hole and a disk of shredded matter and a twisting magnetic field can conspire to fire a beam across the universe, is the key to understanding just how much damage that beam could do if it ever found us. And that is exactly where we turn next. So we have a beam. We have established that a gamma ray burst is not a blast that spreads everywhere, but a searchlight that fires into one narrow cone. Now comes the harder question. The one that turns a strange astronomical curiosity into something you can actually picture. How does a star, in the chaos of its own death, manage to build a machine capable of firing such a beam? Because, make no mistake, a beam this tight, this fast, this precisely aimed, is not a natural byproduct of an explosion. An ordinary explosion is the opposite of focused. It throws debris in every direction at once. To take all that violence and channel it into a needle-thin jet moving at very nearly the speed of light, you need something extraordinary sitting at the center, doing the channeling. You need an engine. And it turns out the universe has two entirely separate ways of building one. The first thing to understand is that gamma ray bursts do not all come from the same kind of event. For decades, as astronomers gathered more and more of them, they noticed that the bursts seemed to sort themselves naturally into two distinct families based on a single, simple property: how long they lasted. Some bursts were over almost before they began, flashing for a fraction of a second up to about 2 seconds, then vanishing. Others lingered, blazing for several seconds, sometimes for minutes. When astronomers plotted all their bursts by duration, they did not get a smooth spread. They got two separate clumps, two populations, with a rough dividing line at around 2 seconds. There were the short bursts, and there were the long bursts. And that simple division in timing turned out to be a clue pointing at two completely different cosmic catastrophes. Two utterly different ways for a star system to die. Let us start with the long bursts, the ones that blaze for several seconds or more, because these are the ones connected to the dramatic image we opened with. The collapse of a single massive star. The mechanism behind them is called the collapsar model, and it begins with a very particular kind of star. Not a star like our sun. Our sun is a comfortable, middleweight star that will end its life quietly, swelling into a red giant and then gently shedding its outer layers to leave behind a small, dense ember. Nothing about the death produces a gamma ray burst. The stars that make long bursts are monsters by comparison, weighing perhaps 20, 30, 40 times the mass of our sun, or even more. These giants live fast and die young. Where our sun will shine for 10 billion years, one of these behemoths burns through its fuel in just a few million, blazing thousands of times brighter and racing toward a far more violent end. When such a star reaches the end, its core, the dense central region where all the fusion has been happening, can no longer hold itself up. Throughout the star's life, the outward push of energy from fusion has balanced the relentless inward pull of gravity. But once the core has fused its way up to iron, that balance is doomed. Because iron cannot release energy through fusion the way lighter elements can. The furnace falters, gravity wins, and the core, which may contain more mass than our entire sun, packed into a ball smaller than a city, collapses inward in a fraction of a second. For the most massive stars, this collapse does not stop at forming a neutron star, the dense remnant left by ordinary supernovae. It goes further. The infalling matter is so heavy that nothing can halt it, and the core collapses all the way down into a black hole, a region where gravity has become so overwhelming that not even light can escape. Now, here is where the engine begins to assemble itself. You might think that once a black hole forms, the story is over, that everything simply falls in and disappears. But the collapse is not clean, and it is not instant. The black hole forms at the very center, but the rest of the enormous star is still there. Layer upon layer of stellar material surrounding the newborn black hole, beginning to fall inward. And crucially, this material is spinning. The original star was rotating, as nearly all stars do, and as its core collapsed, that rotation sped up dramatically in exactly the way a spinning figure skater speeds up when she pulls her arms in close to her body. The conservation of this spinning motion, what physicists call angular momentum, means that infalling matter cannot simply drop straight down into the black hole. It is too much sideways motion. Instead, it swirls around the black hole, forming a flattened, furiously rotating disk of superheated matter, a structure astronomers call an accretion disk. This accretion disk is the heart of the engine, and the conditions inside it defy imagination. Matter is spiraling inward at a significant fraction of the speed of light, packed to extraordinary densities, heated by friction and compression to temperatures of billions of degrees. The disk is feeding the black hole at a monstrous rate, with the equivalent of a substantial fraction of our sun's entire mass being swallowed in a matter of seconds. And as all this matter spirals in and falls toward the black hole, it releases a colossal amount of gravitational energy. This is the fuel source. This is where the staggering power of a gamma ray burst ultimately comes from. The black hole itself is not exploding. Rather, the energy is being liberated by matter falling into it. The way a waterfall releases energy as water drops, except scaled up to a violence that has no parallel anywhere else in nature. But energy alone is not enough to make a beam. A bomb has plenty of energy, and it produces no beam at all. The genius of the engine, the part that turns raw power into a focused jet, comes from two further ingredients: the geometry of the disk and the twisting of magnetic fields. The accretion disk is flat, like a vinyl record with the black hole at the center hole. That means the matter is densest around the disk's plane, the equator of the system, and far thinner above and below, along the rotation axis, near the poles. When the engine starts dumping energy into its surroundings, that energy takes the path of least resistance. It cannot easily blast outward through the dense equatorial disk, which acts like a thick wall of matter pressing in from the sides. But along the poles, above and below, the way is relatively clear, and so the energy is funneled, squeezed, channeled out along those two polar directions, escaping along the rotation axis in two opposite streams. The very shape of the system collimates the outflow into twin jets before they have even fully formed. Then, the magnetic fields take over and tighten the focus even further. The swirling charged matter of the accretion disk, combined with the spin of the black hole itself, generates magnetic fields of phenomenal strength, and those fields get wound up by the rotation into tight, twisting helical structures, like ropes being braided ever tighter. These coiled magnetic fields thread up and out along the poles, and they act like a magnetic nozzle, confining the escaping energy and matter, pinching the outflow inward, keeping it from spreading out as it races away. The combination of the disk's geometry pushing the flow toward the poles and the magnetic fields constricting it into a narrow channel produces something remarkable. Two beams of energy and matter, fired in exactly opposite directions along the rotation axis of the dead star, each one confined to a cone perhaps only a few degrees wide. The engine has built its searchlight, and these beams are not merely fast, they are relativistic, which is a word worth pausing on, because it is the source of much of the danger. The material in these jets is moving at more than 99.9% of the speed of light. Not 90%, not 99%, but 99.9 and several more nines beyond that. At these speeds, the ordinary rules of motion that govern our everyday lives bend and warp under the strange laws of Einstein's relativity. Physicists describe how close something is to light speed using a number called the Lorentz factor. For the matter in your morning coffee, sitting on your table, the Lorentz factor is essentially 1. For a jet in a gamma ray burst, the Lorentz factor can be 100, several hundred, in extreme cases approaching 1,000. A Lorentz factor of 100 means the jet is moving so close to light speed that time itself runs differently for it. Distances contract along its direction of travel, and its energy is multiplied enormously compared to what its raw mass alone would suggest. This near light speed motion does something extraordinary to the beam, something that compounds the focusing we have already described and makes a gamma ray burst appear vastly brighter to anyone in its path. It is called relativistic beaming, and it is one of the most counterintuitive effects in all of physics. When a source of light moves toward you at very nearly the speed of light, the radiation it emits gets dramatically concentrated in the forward direction, swept up and bunched into a tight cone, pointing the way it is traveling. Even if the jet were trying to emit light in all directions, the sheer speed of its motion would gather that light up and hurl it forward into a narrow searchlight. The faster the jet moves, the tighter this forward focusing becomes. So, the gamma rays produced inside a relativistic jet are not just beamed by the geometry of the disk and the magnetic nozzle. They are beamed a second time, even more severely, by the near light speed motion of the material producing them. The result is a beam upon a beam, a focusing on top of a focusing that makes the burst appear to an observer in its path thousands of times brighter than it would if the same energy were simply radiated outward in a sphere. This relativistic beaming is also the reason the burst is so brief and so intense as we observe it. The jet is racing toward us at almost the speed of light, which means it is very nearly keeping pace with the very light it emits. The photons leaving the front of the jet and the jet itself are arriving at almost the same time, compressing what might be a longer event at the source into a sudden, ferocious flash from our point of view. All of that energy gathered and focused and Doppler shifted up into the gamma ray range, the highest energy radiation the universe produces, slams into our detectors in a matter of seconds. The combination of geometric collimation, magnetic confinement, and relativistic beaming is what takes the death of a star and turns it into the brightest explosion in the universe, focused into a single lethal line. It is worth pausing to ask a more basic question that we have so far skipped over. How does the jet actually produce gamma rays in the first place? We have spoken of the beam carrying gamma radiation, but a stream of fast-moving matter is not the same thing as a flash of light. Something has to convert the raw kinetic energy of that near light speed material into the most energetic form of light there is. And the answer reveals one of the more elegant and violent aspects of the whole mechanism. The jet does not flow out smoothly like water from a hose. The central engine is chaotic, sputtering, firing out its material in irregular pulses. Some shells of matter are launched a little faster, others a little slower. And because the whole jet is moving at very nearly the speed of light, a faster shell launched a moment after a slower one will eventually catch up to it and slam into it from behind, deep within the jet, far out in space. These violent internal collisions, shell crashing into shell within the beam itself, are what astronomers call internal shocks, and they are thought to be the source of the prompt gamma-ray flash, the burst proper. The energy of the collision is so enormous, and the material so energized, that it radiates a torrent of gamma rays. The complicated, spiky, irregular profile of a gamma ray burst, the multiple peaks and flickers that so puzzled the early Vela scientists, is the direct signature of this stuttering engine, each spike a fresh collision within the racing jet. The afterglow, by contrast, is produced by a different kind of collision entirely, and understanding the distinction sharpens the whole picture. While the internal shocks happen within the jet, between shells of its own material, the afterglow is born when the leading edge of the jet, having raced out into space, finally plows into the thin gas and dust of the surrounding interstellar medium. The jet acts like a snowplow tearing into a drift, sweeping up the material in front of it, and the resulting collision, the external shock, heats and energizes that swept up matter, which then glows. Because this external collision is a more gradual, ongoing process than the sharp internal smash-ups, it produces the slower, fading, longer-lived afterglow rather than the brief prompt flash, and it produces that orderly march down through X-rays and visible light and radio that we described earlier. Two kinds of collision then, internal and external, account for the two faces of a gamma ray burst. The sudden, spiky flash of gamma rays from shells crashing within the jet, and the slow, fading afterglow from the jet crashing into the surrounding cosmos. The external shock also hands astronomers a remarkable gift, a way to actually measure how narrow the beam is, which is otherwise a maddeningly difficult thing to determine. The trick lies in watching how the afterglow fades over time, because the fading is not perfectly smooth. At a certain point, in many bursts, the afterglow's brightness suddenly begins to drop off more steeply than before, a distinct steepening of the decline that astronomers call a jet break. The reason it happens is subtle and beautiful. Early on, when the jet is moving at its absolute fastest, relativistic beaming is so severe that an observer can only see a tiny patch of the jet's leading edge, a small forward circle, and has no way of telling whether the beam is narrow or wide. The jet effectively looks the same as a sphere from this vantage. But as the jet plows into the surrounding gas and gradually slows, that forward focusing relaxes, and the observer begins to see a wider and wider portion of the jet's face. At the moment when the visible region grows large enough to reach the actual edges of the jet, the geometry changes. The observer realizes there is no more jet beyond those edges, and the afterglow's brightness falls away more sharply. The timing of that jet break, how many days after the burst it occurs, encodes the opening angle of the cone. From it, astronomers can calculate just how narrow the beam was, and it is from exactly this kind of measurement that we know the cones are often only a few degrees wide. The fading light itself, watched carefully over days, betrays the geometry of the gun. There is also a lingering question about the heart of the engine that deserves honest mention, because the picture is not fully settled. Throughout this account, we have placed a black hole at the center, fed by its accretion disk. For many bursts, that is almost certainly the right picture. But there is a serious alternative candidate for the central engine, at least in some cases, a magnetar. A magnetar is a special kind of neutron star, one born spinning incredibly fast and possessing a magnetic field of almost inconceivable strength, far beyond that of any ordinary stellar remnant. Such an object, in the moments after its birth, could in principle act as the engine itself, its furious rotation and titanic magnetic field channeling and powering a relativistic jet without need of a black hole at all. Astronomers are still working out which bursts are driven by newborn black holes and which by these extreme magnetars, and the answer may differ from one burst to the next. What matters for our story is that both routes arrive at the same outcome: a compact, rapidly spinning central object, threading powerful magnetic fields, firing a collimated relativistic beam. The engine has more than one possible heart, but it builds the same searchlight regardless. There is one more wrinkle to the collapser story that is worth appreciating, because it explains why these long bursts are often accompanied by a particular kind of stellar explosion. When the most massive stars die this way, the event is not only a gamma-ray burst, it is also an unusually powerful supernova, sometimes called a hypernova, an explosion considerably more energetic than an ordinary stellar detonation. The jet drilling its way out through the collapsing star, the energy dumped into the star's outer layers by the central engine. All of this can blow the star apart in a spectacularly violent explosion that radiates across the sky for weeks. We need not dwell on the supernova itself, because the explosion is the progenitor, the launching event, not the thing we are focused on. The jet is the subject. But it is worth knowing that long bursts and these superpowered supernovae go hand in hand, two faces of the same monstrous death. And the connection between them was one of the key pieces of evidence that confirmed the collapser model. When astronomers managed to catch the afterglow of certain long bursts and watched the location for the following weeks, they saw the unmistakable signature of a hypernova brightening and fading at exactly the spot the burst had come from. The dying massive star and the gamma-ray jet were one and the same. It is also worth noting that not just any massive star will do. The collapsing star needs to have shed its bloated outer envelope of hydrogen before it dies, so that the jet has a chance of drilling all the way through and escaping into space before the engine shuts off. If the star is still wrapped in a vast puffy hydrogen atmosphere, the jet may stall inside it, smothered before it can break free. The stars thought to produce long bursts are therefore a particular, stripped-down variety known as Wolf-Rayet stars, which have blown away their outer hydrogen layers through fierce stellar winds, leaving behind a dense, compact, rapidly spinning core of heavier elements, almost perfectly engineered to channel a jet out into the universe when the end finally comes. A massive star, spinning fast, stripped bare, collapsing to a black hole, feeding a furious disk, threading a magnetic nozzle, firing a relativistic beam. That is the recipe for a long gamma-ray burst. Now we come to the second family, the short bursts, and here the engine is built from a completely different disaster. The short bursts, remember, are the ones that flash for less than about 2 seconds, often just a fraction of a second. For a long time, their origin was even more mysterious than that of the long bursts, because they were not accompanied by any hypernova, and they often appeared in regions of space where there were no young massive stars to collapse. They were turning up in old galaxies, in places where star formation had long since ceased. where the only stars left were ancient and small. Whatever was making the short bursts, it was not a young giant dying in its prime. It had to be something else, something that could happen even in a quiet, elderly corner of the universe, long after the massive stars had all burnt out. The answer, astronomers came to believe, was a collision. Not the death of a single star, but the violent merger of two stellar corpses. When a massive star dies in an ordinary supernova, without forming a black hole, it leaves behind a neutron star, an object of almost unbelievable density, with more mass than our sun, crushed into a sphere only about a dozen miles across. A teaspoon of neutron star material would weigh billions of tons. These objects are the densest things in the universe, short of black holes themselves. And sometimes, stars are born in pairs. Two massive stars orbiting one another. If both of them die and both leave behind neutron stars, you can end up with two neutron stars locked in orbit, circling each other in the dark. For such a pair, the end is written into the laws of physics from the moment they form. As they orbit, they stir the very fabric of space-time, sending out ripples called gravitational waves that carry energy away from the system. Slowly, over millions or billions of years, this loss of energy causes the two neutron stars to spiral closer and closer together, their orbit tightening, their motion speeding up, and then, in the final moments, after perhaps a billion years of patient inward spiraling, the two neutron stars rush toward each other and collide in one of the most extreme events the universe permits. They merge, and in that merger, they create, at least briefly, a hugely massive, furiously spinning object surrounded once again by an accretion disk of shredded neutron star matter, and very often a newborn black hole at the center. And here is the beautiful and slightly eerie part. Even though the catastrophe is completely different, a collision of two compact corpses rather than the collapse of a single giant, the engine that results is fundamentally the same. You once again have a central compact object, very likely a black hole. You once again have a hot, dense, furiously rotating accretion disk feeding it. You once again have powerful magnetic fields wound up by the rotation. And so, once again, energy is funneled out along the poles, confined by geometry and magnetism, into twin relativistic jets, hurled outward back to back at very nearly the speed of light. The universe builds the same searchlight out of two entirely different kinds of death. A collapsing massive star and a pair of colliding neutron stars, despite having nothing in common in how they begin, arrive in their final moments at one and the same machine. The reason the short bursts are short comes down to the fuel supply. In the collapsar, the black hole has an entire massive star's worth of material to feed on. Layer after layer of stellar matter falling inward over many seconds, keeping the engine running and the jet firing for a relatively long time. In the neutron star merger, there is far less material available. The disk is smaller, formed from the debris of the collision, and the engine consumes its fuel and falls quiet far more quickly. The jet fires, blazes, and is gone in a flash, often less than a second. Different fuel tank, different burn time, but the same fundamental engine producing the same kind of focused, relativistic beam. The merger of two neutron stars also produces its own associated explosion. In the same way, the collapsar produces a hypernova, though this one is gentler and different in character. The collision flings out a cloud of neutron-rich debris that glows for days as exotic, heavy elements form within it, and radioactively decay, a phenomenon called a kilonova. As with the hypernova, we will not dwell on the kilonova itself, because it is the byproduct of the launching event, not the jet we are concerned with. But it deserves a mention, because in the year 2017, humanity witnessed something that confirmed this entire picture in the most direct way imaginable. Detectors on Earth picked up the gravitational waves from two neutron stars spiraling together and merging, the unmistakable tremor of space-time itself as the two corpses collided. And almost at the same moment, telescopes caught a short gamma-ray burst coming from the very same point in the sky, followed in the days afterward by the glow of a kilonova. For the first time, we had caught a neutron-star merger in the act, and watched it fire its gamma-ray jet. Watch the gravitational waves and the gamma rays arrive together. Watch the heavy elements bloom in the aftermath. The short burst engine was no longer a theory. We had seen it work. So now the full picture comes into focus, and it is a picture built entirely around the jet. Two roads, two catastrophes, lead to the same destination. Down one road, a single massive star, spinning fast and stripped of its outer layers, exhausts its fuel and collapses into a black hole, feeding a furious disk that fires a long-lasting beam. Down the other road, two neutron stars, the cold remnants of stars that died long ago, spiral together over eons and finally collide, building the same engine from their wreckage and firing a brief, sharp beam. In both cases, a black hole, a disk of infalling matter, and a twisting magnetic field conspire to take an unimaginable quantity of energy and concentrate it, channel it, and accelerate it to the very edge of light speed, hurling it out into the cosmos as a pair of impossibly narrow jets. And in both cases, relativistic beaming gathers the gamma rays up and flings them forward into a cone so tight and so bright that a single one of these dying systems can briefly outshine everything else in the visible universe to anyone standing in its path. That phrase, standing in its path, it's where the danger lives. We have now built the engine from the ground up. We understand how the beam forms, why it is so narrow, why it moves so fast, and why it carries such monstrous power focused into so small a cone. We have two engines, born of two deaths, both producing the same lethal searchlight. The question that remains is the one that should make the hair on your neck stand up. We have spent all this time understanding the gun. We have examined the barrel, the mechanism, the way it concentrates its fire into a single narrow line. But we have not yet asked what happens at the other end. What happens to a world, an atmosphere, a living biosphere, when that beam stops being an abstract jet racing through empty space and instead sweeps across a planet and locks on? What does the most concentrated explosion in nature actually do when it finds something fragile and alive directly in front of it? That is where we go next, as the beam, at last, finds its target. Imagine then the moment of contact. Somewhere within our own galaxy, a few thousand light years away, a massive star has died, or two neutron stars have collided, and the engine we spent so long building has fired its beam. For thousands of years, that beam has been racing toward us across the dark, a cone of pure gamma radiation, moving at the speed of light. And we have had no warning whatsoever, because the beam moves as fast as any signal that could announce it. There is no flash on the horizon to give us a head start, no rumble of approach. The first thing that happens is also the last warning we get. The beam arrives, and in the space of a few seconds, The sky above one entire hemisphere of the Earth lights up with the most intense flash of high-energy radiation our planet has experienced in its history. Now, here is the first thing that surprises most people, and it matters enormously for understanding the true nature of the threat. The gamma rays themselves never reach the ground. If you were standing outside at the moment the beam struck, you would not be instantly fried where you stand. You would not feel a wave of heat. You would not see the beam. You would not drop dead on the spot. The gamma radiation, for all its ferocity, is stopped high above your head, dozens of miles up, in the thin upper reaches of the atmosphere. The air itself is your shield. The blanket of gas surrounding our planet, which seems so insubstantial when you look up at a clear blue sky, is in fact thick enough, when measured along the path the gamma rays must travel, to absorb essentially all of that radiation before it ever gets close to the surface. So you might be tempted to breathe a sigh of relief. The atmosphere protects us. The danger is blocked. But this is exactly the trap, the fatal misunderstanding, because the gamma rays do not simply get absorbed and disappear harmlessly. They are stopped, yes, but they are stopped by smashing into the atmosphere, and in the process of being stopped, they wreck the chemistry of the air itself. The threat from a gamma ray burst is not that it cooks the surface directly. The threat is far more insidious. It is that the beam destroys the atmosphere's ability to protect us from our own sun. The gun does not kill the planet with its bullet. It kills the planet by shooting away its shield, and then leaving the planet exposed to a slower, more patient executioner that was there all along. It is worth being precise about exactly where in the atmosphere this drama unfolds, because the geometry of it explains why the surface is spared the direct radiation while still suffering the consequences. The gamma rays come in from above, plunging down into the air, and as they penetrate, they encounter more and more atmosphere, denser and denser as they descend. Each gamma ray travels until it happens to strike an atom or molecule and is absorbed, and the deeper into the atmosphere it goes, the more matter there is to strike, so the more likely it is to be stopped. The result is that the gamma rays are absorbed across a range of high altitudes. The bulk of their energy deposited tens of miles up, in the upper atmosphere and the upper reaches of the stratosphere, well above where weather happens, far above the highest clouds, immensely far above the surface where life lives. By the time you get down to the altitudes where mountains rise and aircraft fly, essentially none of the original gamma radiation remains. It has all been absorbed in the thin air far overhead. This is why a person standing outside would feel nothing in the moment. The entire violent transaction happens in a layer of atmosphere so high that from the ground, it might as well be the edge of space. But the absorption of a gamma ray is not a quiet, clean event. And this is the detail that turns a simple blocking into a chemical catastrophe. When one of these immensely energetic gamma rays strikes a molecule high in the atmosphere, it does not merely warm it shatters it. And in doing so, it kicks loose a spray of fast-moving particles, electrons, and fragments hurled outward, carrying much of the gamma ray's energy. Those particles then go on to strike other molecules, breaking them apart in turn and liberating still more particles, which strike still more molecules in a spreading, multiplying chain. A single incoming gamma ray thus triggers not one broken molecule, but a whole cascade of destruction, a shower of secondary particles fanning out through the surrounding air, each one capable of further breakage. This cascade is what allows the energy of the burst to wreck the chemistry of an enormous volume of atmosphere with brutal efficiency. The gamma rays do not have to personally strike every molecule they ruin. They merely have to start the avalanche, and the avalanche does the rest, tearing apart vast quantities of nitrogen and oxygen across the whole illuminated hemisphere in the span of seconds. Some models of a nearby burst add a further, slower layer to this assault, one that arrives not as light, but as matter. Alongside the gamma rays, the same stellar catastrophe and its surrounding shock waves can accelerate a flood of charged particles, cosmic rays, that travel outward through space and may reach the Earth in the months and years after the initial flash, lagging behind the light because they move somewhat slower. These cosmic rays raining down after the burst could prolong and deepen the chemical damage to the atmosphere, extending the assault on the ozone layer well beyond the instant of the gamma ray flash itself. The light arrives first and does the sudden damage. The particles may follow, drawing the injury out over a longer, grinding span. To understand how this works, we need to understand what those gamma rays actually do when they slam into the upper atmosphere. And to understand that, we need to talk about the air itself. The atmosphere is made mostly of two gases. Roughly 4/5 of it is nitrogen, with the nitrogen atoms bound together in pairs, two nitrogen atoms locked into a single molecule. Most of the rest is oxygen, similarly bound into pairs of oxygen atoms. These molecular bonds are strong. It takes a real jolt of energy to break them apart, to tear a nitrogen molecule into its two separate atoms, or to split an oxygen molecule. Under normal conditions, the bonds hold, and the air remains a stable mixture of these paired molecules drifting peacefully around us. A gamma ray is the opposite of peaceful. It is a packet of light carrying an enormous quantity of energy, far more than enough to shatter these molecular bonds. When the beam from a gamma ray burst plows into the upper atmosphere, it is like a hail of microscopic wrecking balls tearing through a structure made of delicate links. Each gamma ray, as it is absorbed, dumps its energy into the air, and that energy goes into ripping molecules apart. Nitrogen molecules are torn into individual nitrogen atoms. Oxygen molecules are split as well. Suddenly, the calm upper atmosphere is filled with a frenzy of broken molecular fragments, free atoms and energized pieces that a moment ago were stable and are now desperate to bond with something, anything, nearby. This shattering of molecules by radiation is called photodissociation, the breaking apart of molecules by light, and a gamma ray burst drives it on a scale the atmosphere has never had to cope with. And here is where the trouble truly begins. Because those freed nitrogen atoms do not simply float around harmlessly, waiting to find their old partners. They are reactive, and they immediately start latching onto oxygen, forming a whole family of compounds that chemists group together under the name nitrogen oxides. These are molecules made of nitrogen and oxygen joined together, and the gamma ray burst manufactures them in staggering quantities, high in the atmosphere, in a matter of seconds. A single strong burst, striking the upper atmosphere, could flood the sky with vast amounts of these nitrogen oxides, creating a chemical contamination of the upper air on a planetary scale. The burst itself lasts only seconds, but in those seconds it seeds the entire upper atmosphere of a hemisphere with a new and hostile chemistry. And these nitrogen oxides are the real weapon. These are what do the lasting damage. Because nitrogen oxides are the natural enemies of ozone. Ozone is a word everyone has heard, usually in the context of the ozone layer, but it is worth being clear about what it actually is and why it matters so much. Most of the oxygen in our atmosphere, as we said, comes as pairs of oxygen atoms. But high up in the atmosphere, in a region called the stratosphere, there exists a thin layer where some of the oxygen takes a different form. 3 oxygen atoms bound together instead of 2. That 3-atom form is ozone. There is not very much of it. If you gathered all the ozone in the atmosphere and compressed it down to the density of the air at the surface, it would form a layer only a few millimeters thick, thinner than a coin. And yet, that wispy, fragile layer is one of the most important features of our entire planet, because ozone has a remarkable property. It is extraordinarily good at absorbing ultraviolet light. Ultraviolet light is a component of the radiation pouring constantly out of our sun. It is invisible to our eyes, more energetic than the visible light we can see, and in large doses it is profoundly damaging to living things. Ultraviolet light carries enough energy to break apart the molecules that life is built from. In particular, it is very good at damaging DNA, the molecule that carries the genetic instructions inside every living cell. When ultraviolet light strikes DNA, it can fracture it, scramble it, introduce errors, and breaks that cause cells to malfunction, to mutate, to die, or to turn cancerous. Every living thing on the surface of the Earth, from the largest animal to the smallest microbe, depends on being shielded from the full force of the sun's ultraviolet output. And the thing that shields us, the thin, invisible barrier standing between all surface life and that sterilizing radiation, is the ozone layer. Quietly, constantly, the ozone in the stratosphere absorbs the dangerous ultraviolet light before it can reach the ground, soaking it up so that only a small, survivable fraction makes it down to where we live. Now you can see the trap closing. The gamma ray burst floods the upper atmosphere with nitrogen oxides. And nitrogen oxides destroy ozone. They do it through a particularly vicious chemical process, the kind that makes them so much more dangerous than their quantity alone would suggest. A nitrogen oxide molecule can attack a molecule of ozone, strip away one of its oxygen atoms, and break the ozone apart. That much would be bad enough. But the truly devastating feature is that the nitrogen oxide is not consumed in the process. It is a catalyst. After it destroys one ozone molecule, it is regenerated, set free again, ready to attack another ozone molecule, and then another, and then another. A single nitrogen oxide molecule can go on to destroy enormous numbers of ozone molecules, cycling through the reaction over and over, a chemical assassin that is never used up. This is what chemists mean by a catalytic cycle, and it is why a relatively modest amount of nitrogen oxides can chew through a vast amount of ozone. The contamination from the burst does not just punch a hole in the ozone layer once. It sets loose a self-renewing chemical machine that keeps grinding the ozone down long after the burst itself is over. In the aftermath of a nearby gamma-ray burst, models suggest the ozone layer over much of the planet could be severely depleted, with a substantial fraction of it destroyed. We are not talking about the localized seasonal thinning that occurs naturally over the poles. We are talking about a planet-wide collapse of the ozone shield, a global stripping away of the barrier that has protected surface life for hundreds of millions of years. And the gamma rays from the burst would have struck only one hemisphere directly, the side of the Earth facing the source at that moment. But here's a cruel detail. The damage does not stay confined to that hemisphere. The upper atmosphere is not still. Air circulates, winds blow, the stratosphere mixes itself around the globe over the following weeks and months. The cloud of ozone-destroying nitrogen oxides, born on the side that faced the beam, spreads outward, carried by atmospheric circulation across the entire planet. There is no safe hemisphere. There is no far side to hide on. Within a relatively short time, the entire globe finds itself living under a shredded and failing ozone layer. And there is something else the nitrogen oxides do, beyond destroying ozone, that adds a strange and ominous visual to the catastrophe. Some of these nitrogen oxide compounds are coloured. Nitrogen dioxide, in particular, is a reddish-brown gas. In large enough quantities, spread through the upper atmosphere, it would tint the sky itself. The brilliant blue we are used to could turn murky, brownish, dimmed. A haze of this reddish-brown compound high overhead would actually block out a fraction of the incoming sunlight, casting the world into a kind of dimness. So the aftermath of a gamma-ray burst would not be a bright, scorched sky. It would be a darkened, discoloured one. A sky gone the colour of rust and smog, filtering the sun's light through a veil of the very chemicals that were, at the same moment, dismantling the planet's protection against that sun's most dangerous rays. The heavens themselves would change colour, and the change would be a sign of the shield failing. Let us be clear about the timeline, because this is what makes the gamma ray burst such a peculiar and terrible kind of threat. The burst itself is over in seconds. By the time you notice anything was wrong, if you notice anything at all, the beam would have already passed. There would be no ongoing bombardment, no continuing assault from space. The gun fires once and falls silent. But the damage it does is not over in seconds. The damage is only beginning. The nitrogen oxides it created remain in the upper atmosphere, and they do not vanish quickly. The catalytic destruction of ozone continues for months. The depleted ozone layer takes years, possibly many years, to rebuild itself, because the natural processes that make ozone are slow compared to the speed at which the burst tore it down. For a period of years then, the surface of the Earth would be bathed in far more ultraviolet light than at any time in the planet's recent history. The burst is an instant. Its consequences are a long, slow season of exposure. It is worth dwelling on why the recovery takes so long, because the imbalance between how fast the ozone is destroyed and how slowly it is rebuilt is central to the scale of the disaster. Ozone is not a permanent fixture of the atmosphere. It is constantly being created and constantly being destroyed in a natural, ongoing balance. High in the stratosphere, ultraviolet light from the sun routinely splits ordinary oxygen molecules apart, and the freed oxygen atoms bond with other oxygen molecules to form ozone. At the same time, ozone is always being broken back down by various natural processes. Under normal conditions, creation and destruction sit in a steady equilibrium, maintaining that thin protective layer at a roughly constant thickness over time. The making of ozone, though, is a slow and gradual business, dependent on the steady, patient action of sunlight working through the atmosphere over long stretches of time. A gamma ray burst shatters that equilibrium with brutal speed. In seconds, it manufactures the ozone-destroying nitrogen oxides, and those nitrogen oxides, through their relentless catalytic cycling, tear down ozone far faster than the slow natural processes can replace it. Worse, the nitrogen oxides linger. They are not consumed in their attack on the ozone, remember, but regenerated again and again, so they persist in the upper atmosphere for a long time, continuing the destruction month after month. Only gradually do they get swept out of the stratosphere by the slow circulation of the air, drifting downward and eventually being removed. So you have a fast, savage destruction of ozone paired with a slow, patient rebuilding, and the ozone layer cannot recover until the lingering nitrogen oxides have finally cleared and the gentle ozone-making machinery has had years to catch up. The wound is inflicted in an instant and healed over the better part of a decade. For that entire stretch, the shield remains thin, and the ultraviolet light keeps pouring through. We should also be precise about what that increased ultraviolet light actually means at the surface, because the danger lies in a particular slice of the sun's output. The most biologically damaging ultraviolet light, the kind most effective at breaking apart the genetic molecule and harming living cells, is the very kind that the ozone layer is most responsible for absorbing. Under a healthy ozone layer, only a small, survivable fraction of this radiation reaches the ground, and life has adapted comfortably to that level over hundreds of millions of years. Strip the ozone away, and the amount of this damaging ultraviolet light reaching the surface can multiply several-fold. What matters to a living cell is the total dose it accumulates, and with the radiation arriving several times more intensely, the dose that once took a whole day to absorb might now be delivered in a fraction of that time. For an organism that cannot hide, that has no way to reduce its exposure, the difference between a tolerable daily dose and a lethal one is exactly this kind of multiplication. And it is precisely what a stripped ozone layer would impose on every exposed living thing across the planet. Day after day, for years. And now we arrive at the part of the story where the threat finally reaches the ground, not as gamma rays, but as the sun's own ultraviolet light, pouring through the broken shield. With the ozone layer severely depleted across the entire globe, the ultraviolet radiation reaching the surface would climb to levels that life is simply not adapted to endure. Step outside under that sky, and you would be exposed to ultraviolet light many times more intense than anything experienced under a normal sun. The amount of time it would take to receive a serious, damaging burn would shrink dramatically. But sunburn on human skin, while vivid, is far from the heart of the catastrophe, because humans can take shelter. We can stay indoors, cover ourselves, hide from the sky. The creatures that cannot hide are the ones that matter, and it is in the web of life as a whole that the true devastation would unfold. Consider where so much of life's foundation actually sits. Not in the large animals we tend to think of first, but in the smallest organisms, the ones at the very base of the food chains that everything else depends on. In the oceans, the surface waters are home to phytoplankton, microscopic floating organisms that drift in the sunlit upper layer of the sea. These tiny organisms are extraordinarily important. They are the grass of the ocean, the base of the entire marine food web. Nearly all life in the sea depends, directly or indirectly, on phytoplankton, which capture the sun's energy and turn it into food that ripples upward through every creature in the ocean, from the smallest fish to the largest whale. And phytoplankton live precisely where they are most vulnerable, floating in the topmost layer of the water, soaking up sunlight, with no shell to crawl into and no shade to seek. They cannot dive deep to escape, because they need the light to live. Under a sky stripped of its ozone, the surface waters of the ocean would be flooded with ultraviolet radiation, and the phytoplankton would be exposed to it directly, their DNA damaged, their populations potentially devastated. If the base of the ocean food web were to collapse, the consequences would climb up through every level above it. The tiny creatures that eat phytoplankton would starve, The small fish that eat those creatures would follow. The larger fish, the seabirds, the marine mammals, every link in the chain that ultimately traces back to those microscopic organisms would feel the loss cascading upward. A blow struck at the smallest, most vulnerable level of the ocean propagates through the entire structure of marine life. The same logic applies on land. Plants, the base of food chains on land, would be exposed to the same punishing ultraviolet glare. Their growth stunted, their tissues damaged, their ability to feed the animals that depend on them compromised. Insects, many of which are sensitive to the ultraviolet light, could suffer enormously, and the loss of insects would ripple through every ecosystem they support, from the plants they pollinate to the animals that eat them. This is the crucial insight about how a gamma ray burst threatens a living world. It does not need to kill organisms directly with its radiation. It does not need to reach down and touch a single living thing. All it has to do is destroy the ozone layer and then step back and let the sun do the rest. The burst removes the shield, and the planet's own star, the same sun that has nurtured life for billions of years, becomes the instrument of destruction. Its ultraviolet output, normally filtered to a survivable trickle, now raining down unfiltered onto a world that has no defense against it. The damage works its way up from the bottom, from the microbes in the plants and the smallest organisms, hollowing out the foundations on which all larger life rests. It is a slow-motion catastrophe set in motion by an event that lasted only seconds. There is a further turn of the screw to consider as well. The same nitrogen oxides that destroy the ozone and tint the sky brown can also have other atmospheric effects. By dimming the sunlight reaching the surface, the brownish haze could cool the planet, at least temporarily, disrupting climate and weather patterns. Some of the nitrogen compounds could eventually rain out of the sky in forms that alter the chemistry of the land and water below. A kind of acidic fallout settling over the surface in the months after the burst. The full picture is of a planet whose atmosphere has been thrown into chemical chaos all at once. The protective ozone collapsing, the sky discolored and dimmed, the surface alternately flooded with ultraviolet light and chilled by haze, the rains carrying down altered chemistry, and the whole tangled web of life reeling under stresses it has no evolutionary memory of, and no ready defense against. It is worth pausing to appreciate just how strange and specific this threat is, because it is unlike almost any other cosmic danger you might imagine. When people think of threats from space, they usually picture an asteroid, a great rock slamming into the Earth, throwing up dust, igniting fires, a blunt and physical catastrophe. A gamma-ray burst is nothing like that. It is silent. It is invisible. It strikes without impact, without sound, without any physical object touching the planet at all. It does its work not through force, but through chemistry, reaching into the delicate molecular machinery of the upper atmosphere and rearranging it, turning the planet's own shield into a source of vulnerability and the planet's own sun into a threat. There is no crater, no debris, no smoking ruin to mark where it happened. There is only a sky that has changed colour, an ozone layer that has quietly failed, and a slow rising tide of ultraviolet light washing over a world that just seconds before had been perfectly safe. And everything about this threat, every link in this terrible chain, traces directly back to the beam. It is only because the energy of a gamma ray burst arrives, concentrated, focused all at once into a narrow cone, that it can overwhelm the atmosphere's chemistry so completely. A more diffuse source, Spreading the same energy gently across the whole sky over a long time would do far less damage because the atmosphere could absorb it gradually, could heal as fast as it was harmed. It is the suddenness, the intensity, the sheer concentration of the beam that makes it lethal, dumping more energy into the upper atmosphere in a few seconds than that atmosphere can possibly cope with, shattering molecules faster than they can reform, manufacturing ozone-destroying chemicals in quantities that take years to clear. The beam is the threat. The focus-in is the danger. Everything we learned about how the jet forms, how it narrows, how relativistic beaming concentrates its fury into a searchlight, all of it comes home in this moment, in the chemistry of a poisoned sky. So we have followed the beam from its birth in the death of a star all the way to its arrival at a living world. And we have seen what it does. Not a direct killing blow, but the silent removal of a planet's protection, followed by the slow, patient devastation wrought by its own sun pouring through the gap. We have seen the ozone layer collapse, the sky turn the colour of rust, the ultraviolet light flood down onto the most vulnerable organisms, and the damage climb upward through the food chains until the whole structure of life is shaking. The picture is grim, and it raises an obvious and urgent question. If a nearby gamma-ray burst could do all of this, could strip the ozone and flood the surface and cripple the base of the food web across an entire planet, then could such an event push a world's biosphere past the breaking point entirely? Could it cause not just damage, but a mass extinction, a great dying that reshapes the history of life itself? And if so, has it ever actually happened, here, on this very planet, in the deep history of the Earth? That is the question we turn to next, along with the one that matters most of all to anyone living under this sky. How likely is any of it really to happen to us? We ended with a question that should weigh on anyone who has followed this far. If a nearby gamma-ray burst can strip away a planet's ozone, flood its surface with ultraviolet light, and devastate the foundations of its food web, could such an event do more than wound a world? Could it kill on a planetary scale? Could a single beam, fired from a dying star thousands of light years away, reach across the dark and trigger a mass extinction? One of those rare and terrible chapters in the history of life, when a huge fraction of all living species vanish from the record at once? And the honest, careful answer is this: it is plausible. It is genuinely possible. And there's one moment in the deep past of our own planet where some scientists have wondered, seriously and openly, whether exactly this might have happened. But I want to be very clear about the nature of that wondering, because this is precisely the kind of idea that gets exaggerated. And the truth is more interesting than the exaggeration. To understand the idea, we need to travel back in time, far further than dinosaurs, far further than the first creatures crawled onto land, to a period called the Ordovician, which unfolded roughly 450 million years ago. This was a world that would seem deeply alien to us. There was very little life on land yet, perhaps only the simplest of plants beginning to gain a foothold. The great drama of life was playing out in the oceans, which teemed with an extraordinary variety of creatures. There were trilobites, those segmented, armoured animals that scuttled along the sea floor. There were early corals building reefs. Strange shelled creatures, primitive fish just beginning to appear, and vast clouds of tiny organisms drifting in the sunlit surface waters. It was a rich, thriving, complicated marine world, one of the most biologically diverse the planet had yet seen. And then, around 445 million years ago, something went terribly wrong. Over a relatively short span of geological time, a huge fraction of all the species in those oceans died out. This event, the End Ordovician extinction, was one of the 5 greatest mass extinctions in the entire history of life on Earth, ranking among the very worst die-offs the planet has ever endured. Something like 8 out of every 10 species, by some estimates, vanished. The trilobites were hit hard, the reefs collapsed, entire branches of the tree of life were pruned away. It was a catastrophe of the first order, a genuine turning point in the story of life, and like all such turning points, it has drawn intense scientific scrutiny as researchers try to work out what could possibly have caused such widespread death. Now, here is where we must be careful, because the mainstream scientific understanding of the End Ordovician extinction does not, in fact, point to a gamma-ray burst at all. The leading explanation involves climate. The evidence in the rocks suggests that around the time of the extinction, the planet plunged into a severe ice age. Great ice sheets spread across the southern lands, sea levels dropped dramatically as water was locked up in ice, ocean currents and chemistry shifted, and the shallow coastal waters where so much marine life flourished were drained and disrupted. A rapidly cooling world, falling sea levels, changing ocean conditions, these are the factors that most scientists believe drove the End Ordovician extinction. It is, in the conventional view, a story about climate and the sea, not about a beam from space. That is the baseline you should hold in your mind. The default, best supported explanation is terrestrial and climatic. But here is where the gamma-ray burst idea enters, and why some scientists found it intriguing enough to propose. A number of years ago, a group of researchers raised a provocative possibility. What if, they asked, a gamma-ray burst played a role in triggering or worsening that ancient catastrophe? Their reasoning was based on the very chain of effects we have spent this whole story building. We know that a nearby burst would shred the ozone layer. We know that it would flood the surface and the upper ocean with ultraviolet light. And we know that the creatures most vulnerable to ultraviolet light are precisely the small organisms living in the sunlit surface waters of the sea, the very base of the marine food web. The researchers noticed something suggestive in the pattern of the Ordovician die-off. The extinction seemed to fall especially hard on creatures that lived in the upper, sunlit layers of the ocean and in shallow waters, while some deeper dwelling creatures fared comparatively better. That is, broadly, the kind of pattern you might expect if a sudden pulse of ultraviolet radiation had swept the planet, striking hardest at the surface dwellers and sparing those shielded by deeper water. They went further and pointed out that the ultraviolet flood could even help explain the climate connection. Remember the brownish nitrogen oxides that a gamma-ray burst manufactures? The ones that tint the sky and dim the sunlight? A sufficiently severe burst, by filling the upper atmosphere with these light-blocking compounds, might cool the planet, perhaps even helping to nudge a vulnerable world toward an ice age. So in this hypothesis, the burst is not merely an alternative to the climate explanation, it might be a trigger for it. A single cosmic event that both strips the ozone and helps tip the climate into its deadly cooling, weaving the radiation story and the ice age story together into one. It was an elegant, intriguing idea, and it captured the imagination, because it connected the deep history of life on Earth to the violent deaths of distant stars. And yet, intriguing as it is, this remains a hypothesis, and it is important to treat it as exactly that. There is no smoking gun. There is no direct evidence in the Ordovician rocks that says a gamma ray burst struck the Earth. The pattern of the extinction is consistent with a burst, but consistency is not proof, and the same pattern can be explained by the climate and sea level changes alone without any need to invoke a beam from space. A gamma ray burst, by its very nature, would leave little obvious trace. It deposits no crater, scatters no debris, embeds no exotic layer of unusual elements in the rock the way a giant asteroid impact does. Its fingerprint would be subtle and chemical and largely erased by the passage of 445 million years. So, we are left in a genuinely uncertain position. It could have happened. The idea is scientifically respectable and worth taking seriously, but it has not been confirmed. It is not the leading explanation, and no responsible account should claim that a gamma ray burst is known to have caused the end Ordovician extinction. What we can say is that such a burst could in principle cause a mass extinction, and that one ancient die-off bears a pattern loosely consistent with the idea. That is the honest shape of our knowledge, and it is enough to make the question fascinating without pretending to an answer we do not have. This naturally raises a broader question that scientists have genuinely pursued. Is there any way to catch a gamma ray burst in the act of having struck the Earth, not by inference from an extinction pattern, but by finding its actual chemical fingerprint preserved somewhere in the planet's record? If a burst really did flood the atmosphere with nitrogen oxides, after all, some of those compounds would eventually have rained down out of the sky and settled onto the surface, and in principle, a sudden, sharp spike of such compounds might be locked away in layers that preserve a year-by-year history of the atmosphere. The most promising archives are things like ice cores, the long cylinders of ancient ice drilled from the great ice sheets, in which each annual layer traps a sample of the air and fallout of its time, building a calendar of the sky stretching back many thousands of years. A burst that struck within that span might, just possibly, have left a telltale layer enriched in nitrogen-bearing compounds, a chemical scar marking the year the beam arrived. The trouble is that such a signature would be devilishly hard to identify with any confidence, and this is where we have to be candid about the limits of the method. Nitrogen compounds rain down onto the ice for all sorts of ordinary reasons. Lightning produces them. Other events disturb the atmosphere and leave their own marks. So even if a sharp spike of the right chemistry were found in an ice layer, distinguishing a genuine gamma ray burst from the many mundane causes of such a spike would be extremely difficult. A single anomalous layer proves very little on its own. And for the truly ancient events, like the end Ordovician extinction we have been discussing, the problem is far worse, because there is no ice that old. The great ice cores reach back, at most, a few hundreds of thousands of years, a mere sliver of geological time, nowhere near the hundreds of millions of years that separate us from the Ordovician seas. For events that deep in the past, the atmospheric record we would need has long since been destroyed, recycled away by the endless churning of the planet's surface. So the hunt for a direct chemical fingerprint of a past burst remains, for now, inconclusive. Scientists have looked, and continue to look, for anomalies in the record that might betray such an event, but no clear, undisputed signature has been found that everyone agrees points to a gamma ray burst rather than to some ordinary terrestrial cause. This is not a failure so much as a reflection of just how subtle and elusive the mark of a burst would be. The very quietness that makes a gamma ray burst so different from an asteroid impact, the absence of a crater or a scattered layer of exotic debris, is exactly what makes its passage so hard to confirm long after the fact. So, let us set the deep past aside and turn to the question that matters most to those of us living now, under this sky, today. How worried should we actually be? If a gamma ray burst could do all of this, if it could in principle end a great deal of life on a planet, then how likely is it that one will do this to us, here, any time that matters? And this is where, having spent so long building up the menace of these objects, I get to offer you something close to reassurance, grounded not in wishful thinking, but in the actual physics of the situation. Because when you work through the real requirements for a gamma ray burst to threaten the Earth, you find that the conditions are remarkably demanding, and the odds, while never quite zero, are reassuringly long. The first requirement is distance. A gamma ray burst is mind-bendingly powerful, but power falls off with distance, and even something this violent becomes harmless if it is far enough away. The vast majority of the bursts we detect occur in distant galaxies, billions of light years from us, and at those distances they pose no threat whatsoever. By the time their energy has spread across billions of light years of space, it arrives at Earth as a faint flicker in our instruments. Interesting to astronomers, utterly irrelevant to life. For a burst to do real damage to our ozone layer, it would need to be inside our own galaxy. And not merely inside our galaxy, but relatively close within it. The estimates vary, but the danger zone is generally thought to extend out to something on the order of a few thousand light years, with serious ozone-stripping damage requiring a burst within perhaps 6,000 light years or closer, and the most catastrophic effects demanding something considerably nearer than that. Beyond that range, the beam, even aimed directly at us, would have spread and weakened enough that the atmosphere could largely shrug it off. Now, a few thousand light years might sound like a lot of room for a dangerous star to lurk, and our galaxy does contain a great many stars within that distance. But here is the second requirement, and it is the one that truly transforms the odds, because it brings us back to the central idea of this entire story: the beam. A gamma ray burst does not shine in all directions. It fires into a narrow cone, just a few degrees wide, and that cone must be pointed almost exactly at us for the beam to strike the Earth. This is an extraordinarily stringent condition. Imagine a star within the danger zone reaching the end of its life and firing its twin jets in some random orientation with no particular regard for where the Earth happens to be. The chance that one of those narrow cones, just a few degrees across, happens to be aimed precisely in our direction is small. The jets could point in almost any direction, and the overwhelming majority of those directions miss us completely. For every burst that could threaten us, there are many more, even nearby ones, whose beams sweep harmlessly off into other parts of space, never touching the Earth at all. So a dangerous burst requires two independent strokes of bad luck to coincide. It must happen close enough, within a few thousand light years, and its beam must happen to be aimed almost exactly at us. Each of these conditions alone is unlikely. Together, they become rare indeed. And there is a third condition that stacks the odds even further in our favor, having to do with what kinds of stars produce these bursts in the first place. Recall that the long bursts, the most energetic and longest lasting kind, come from the collapse of very particular massive stars. The stripped down Wolf-Rayet variety, spinning rapidly, having shed their outer layers. Such stars are not common to begin with. Massive stars of any kind are vastly outnumbered by ordinary stars like our Sun, and the specific configuration needed to produce a powerful long burst is rarer still. What is more, there is reason to think the most powerful long gamma-ray bursts prefer a particular kind of environment, one that is increasingly rare in a galaxy like ours. The production of these energetic bursts seems to be favored in regions where the stars are poor in heavy elements, what astronomers call low metallicity. In the early universe and in galaxies that have not been enriched by many generations of stellar deaths, stars formed with very few elements heavier than hydrogen and helium, and these element-poor stars appear to be more efficient at producing the kind of fast-spinning collapse that fires a strong jet. Our Milky Way, by contrast, is a mature, well-enriched galaxy. Billions of years of star formation have seeded it thoroughly with heavier elements. And our particular corner of it, where our Sun resides, is comparatively rich in these elements. This makes our neighborhood a relatively unfavorable place for producing the most dangerous long bursts. We live, in a sense, in a quiet and chemically settled suburb of the galaxy, far from the kind of element-poor, vigorously star-forming environments where powerful bursts are most likely to be born. Our location helps in another way as well. Our solar system sits a good distance out from the crowded, chaotic center of the Milky Way, well over halfway from the core toward the edge, in a relatively calm region between the galaxy's grand spiral arms. The spiral arms and the galactic center are where star formation is most intense, where massive stars are born and die most frequently, where the violence is concentrated. We are not in the thick of it. We are off to the side, in a region where the stars are more sparsely scattered, and the rate of catastrophic stellar deaths is lower. All of these factors compound: the rarity of the right kind of star, the demanding requirement of proximity, the stringent requirement of beam alignment, and our fortunate position in a well-aged, element-rich galaxy unlikely to forge such a weapon nearby. When you put them together, the conclusion is that a civilization-threatening gamma ray burst striking the Earth is an extraordinarily improbable event on any time scale that human beings need to worry about. The best estimates suggest that a nearby burst aimed at us might occur only once in many hundreds of millions of years, perhaps even less often, comparable to or rarer than the great extinction-causing events of the past. Of course, the natural question that follows is whether there is any specific star out there that we should be nervously watching. Any loaded gun pointed in our general direction. And here it is worth addressing the most famous candidate, the red giant star that people often bring up in this context, Betelgeuse. Betelgeuse is one of the most recognizable stars in our night sky, a brilliant reddish point of light marking the shoulder of a well-known constellation. It is a massive star, far larger than our Sun, and it is genuinely nearing the end of its life. Within the next 100,000 years or so, an eye blink in cosmic terms, Betelgeuse is expected to die in a spectacular supernova explosion, an event that will briefly make it one of the brightest objects in our sky, visible even in daylight. It is, understandably, the star people point to when they ask whether we are in danger. But Betelgeuse is not, in fact, a threat to us. And the reasons why are a perfect illustration of everything we have learned. First, although it is reasonably close by stellar standards, it is far enough away, several hundred light years distant, that even a powerful event there would do little harm to our atmosphere. Second, and more importantly, Betelgeuse is not the kind of star expected to produce a gamma-ray burst at all. When it dies, it will most likely die in an ordinary, if dramatic, supernova, not in the special fast-spinning collapse that fires a relativistic jet. The conditions for a burst are particular, and Betelgeuse does not appear to meet them. And third, even in the extremely unlikely event that it did produce a burst, the orientation matters. Its rotation axis, along which any jets would fire, is not pointed at us. The beam, if there ever were one, would miss. So the most famous nearby dying star, the one most likely to make people anxious, turns out on examination to be no danger to us whatsoever. It will give us a magnificent show when it finally explodes, a once-in-many-generation spectacle, and it will do so without the slightest harm to the Earth. The very fact that the scariest candidate we can name is so thoroughly harmless tells you a great deal about how rare a real threat would have to be. There is something worth sitting with in all of this, a perspective that emerges once the fear has been put in its proper place. We have spent this whole journey contemplating one of the most violent and powerful phenomena the universe is capable of producing, an event so energetic it can outshine entire galaxies, so lethal it could in principle scour the life from a world. And the universe does produce these events, constantly, all across the cosmos, their beams crisscrossing the dark in every direction. We live, it turns out, in a universe that is capable of genuine catastrophe, where the death of a distant star can, in theory, reach across thousands of light years and touch a living world. That is a sobering thing to know. And yet, when we look carefully at our own situation, at the particular galaxy we inhabit, the particular neighborhood we occupy, the particular requirements such a catastrophe would demand, we find ourselves remarkably, almost improbably, safe. The threat is real in principle and vanishingly unlikely in practice. Both of these things are true at once, and holding them together is the beginning of wisdom about our place in the cosmos. It is worth appreciating, too, the strange chain of dependencies that protects us, because our safety is not a single thing, but a layering of fortunate circumstances. We are protected by distance, by the sheer emptiness of space that dilutes even the most violent event into harmlessness across enough light years. We are protected by geometry, by the narrowness of the beam that makes it overwhelmingly likely to miss any particular target, including us. We are protected by chemistry, by the maturity of our galaxy and the richness of our local elements that makes our neighborhood an unlikely birthplace for the deadliest bursts. We are protected by location, by our quiet position far from the galaxy's violent heart, and in the moment of any actual encounter, we would even be partly protected by the atmosphere itself, which absorbs the gamma rays before they reach the ground, taking the blow on our behalf, even as it suffers the chemical wounds we have described. Layer upon layer of circumstance stands between us and disaster, and while no single layer is a guarantee, together they make for a sky that is, on any human timescale, profoundly and reliably safe. And there is a final thought to carry away from all of this, one that reframes the whole subject in a gentler light. The same physics that makes a gamma ray burst so dangerous, the focusing of the beam, the relativistic engine, the violence of stellar death, is also the physics that makes these objects visible to us across almost the entire span of the observable universe. We can detect bursts from so far away, from the very edge of what we can see, precisely because they're so concentrated and so bright. This means that gamma ray bursts are among our most powerful tools for studying the distant cosmos. Beacons that light up the deep past, allowing us to probe the universe as it was billions of years ago, to study the deaths of the very first generations of massive stars, to map the history of star formation across cosmic time. The same beam that could end the life of a world is also a lantern held up across the darkness, illuminating regions of space and time we could never otherwise reach. The most lethal phenomenon in nature is also one of the most illuminating, in the most literal sense. What could destroy is also what reveals. So when you look up at the night sky, at those countless quiet points of light, you can hold in your mind the full truth of what you now understand. Out there, scattered across the universe, stars are dying and remnants are colliding, and each time one does, it can fire a searchlight of pure energy across the cosmos, a beam so powerful it could end the life on a world unlucky enough to lie in its path. These beams are real, and they are firing right now in every direction all across the universe. It is a genuinely dangerous cosmos in which we find ourselves. And yet, by an extraordinary convergence of distance and geometry and chemistry and location, we sit beneath a sky that has sheltered life on this planet for billions of years and will, in all probability, go on sheltering it for billions more. The guns are out there. The barrels are real. But they point, almost always, somewhere else, and the few that might ever point our way are rare beyond easy reckoning. We live in a universe capable of catastrophe, on a small world that has, against considerable odds, been spared. And understanding both halves of that truth, the danger and the safety together, is perhaps the closest we can come to seeing our place in the cosmos clearly. The beam is the whole story. From the death of a star, to the chemistry of a poisoned sky, to the long, fortunate quiet of a world that the searchlight has so far always missed.